What's coming off around here?
If you guys playing railroad anymore today, there's a landslide, a new cut.
Welcome to Fun with HO Scale Stuff. This is going to be episode 18, which will be part 3 of the JMRI via Bluetooth serial. Previously in this series, I was able to establish the necessary Bluetooth COM port on my damaged PC. In this part 3, I'm going to examine the RS-485 serial data from the NCE Power Cab and characterize that signal. Well, as many of you are familiar with the NCE cab control system, you know that in order to actually use it, it's necessary to apply power to the control. And the way that's done is through the power supply using this interface that they've made. It's nothing more than some connectors. The power for it is applied on this barrel connector, which comes from the power supply that they supply with it. And of course that would get plugged in. This gets plugged into here. And you might say, well, why don't they just plug it into the cab controller? And the reason for that is that their design was created so that they can support more than one cab control, so that up to 4 people can be able to independently control DCC powered locomotives on the same track. And how does that work? Well, NCE engineers, what they did was they've got in this handheld unit the actual controller which creates the DCC AC square wave for the track, and that will be on this connector on 2 of the conductors in this cable. And in order for them to control, well, first of all, in order for them to gain power, it's routed by plugging the NCE connector, the cab connector, into the left side connector on the front of this panel. So it goes in just like that. Now what this means is that the power is routed to all 4 of these connectors that are shown on this board. And on the front, you can get access to an extra cab, but they don't tell you precisely how that works. What I will propose is what's happening is that because they said there's 4, and also in the documentation, they say that cab addresses 1, 2, 3, and 4 are reserved. And this one is 1. And so what I'm suggesting then, and we'll take a look and find out, is that the power is routed to all 4 connectors so that any cab controller that gets plugged into any of the 3 free ones is going to get power as well from the power supply. Excuse me, get that out of there, from this power supply. And also I suggest that what they do is they use a protocol on an additional 2 wires. So 2 wires are going to be 2 leads in this cable are for the DCC AC square wave that this cab control is producing using the DCC controller that's built into it. But there's also an interface function that's built that will take any one of the user commands from this cab and convert it into a command that is sent to the controller which is producing the DCC signal. So the DCC signal is always coming from the master cab controller. So, and any one of the additional cab controllers will also be receiving its power from here, but it will also be able to talk to this interface control, which apparently has a polling unit or a control that allows other controllers to speak as well to the DCC controller that's built into this. And what that means is that there's two conductors here for the DCC square wave. There are two conductors for the DC power, and then there are two conductors for what I'm calling this local network. And it's apparently because of the addresses of that claim each controller has to have an address 1, 2, 3, or 4, so that it's an addressable type of network. Maybe something very much like RS-485. I don't know for sure, but I'm going to find out. And that would be the other two conductors. So there's 6 conductors that are in this cable. I just happen to have the jack that goes into here, wherein the two conductors that are pinched into the jack conduction, the conductor here, are the two that I suppose are being used as a local area network. So I can plug that into this carefully, since I don't want any shorts going on here. That would probably damage the main controller. And also, this signal will be some kind of differential signal. I'm expecting it's a square wave, DC square wave, and I'm suspecting that it's got a particular baud rate, and I'm suspecting that there's packets of pulses, that each pulse being some kind of bit. That's what I propose it is. And so because of that, as I have a scope, and I can take the scope and I can connect it to the 2 leads that I freed up on this short cable that's plugged in. But because of differential signal, I have to isolate the scope. I don't want the scope ground on the return. So I can get a signal using one probe by hooking a ground lead to one side. So looking at a differential signal, and then the probe lead to the other side to make sure that they don't touch. Very careful about that. Come on, get over there. Okay, and then I'll isolate the scope power. So it's currently plugged into a power strip back there. I'll plug this on the I'll isolate the plug, and I'll power up the scope, and then I'll turn this on and supply it. I'll supply it power, and we'll see what we get. Let's take a look. The next phase of investigating this connection possibility would be to consider right now what are the chances or the opportunities to connect a serial link to the NCE Power Cab. Since this Power Cab has the actual control hardware that generates the DCC signal going to the track, it must be able to, as I've already pointed out, see commands coming from an additional controller. And so, as previously stated, this cable going to the additional controller has only 4 signal leads, 4 conductors within that cable. And so 2 of those conductors, as I've said, must be some form of RS-485 signal that's being communicated back and forth between this device, the main power cab, and the additional controller, which in this case is going to be the Bluetooth serial channel. So in order to gain some insights into what does this signal look like right here, pardon me, I'm going to take a look at it with the scope. I'm going to use the scope to look at that. And so I'm going to use the connector device that they supply with the power cab, pardon me again, sorry, and using this extra cab, I've got this connector I made that has leads going only to these two, not the DC power source, but just these two signals that I think are the RS485 signals. So that will go. So that will go here. I'll get it in there. There it is. Okay. And then I'll take my scope and I'll connect it across these two leads to get a picture of what that signal looks like. So for the power cab itself, I need to bring that into the equation. Yes, power cab, and we'll want to power that. Power cab has to be able to see the signal, or create the signal, that is. So the power cab, I'm saying the power cab is actually creating the signal that is going to be visible on this extra cab. So the only other thing that we need here is we need to plug the power supply in. So I don't know if you can see that. That's the power supply. It's on a power strip. So let's just do that. And of course that plugs into here, into the barrel connector. Turn that off. So I've got power now. That would be also here, but of course we don't care about that. We're not looking at the power on here. It's power right now to the power cab. And I have the scope probes hooked up. And this is the plug for the oscilloscope. And what I've done here is I've isolated ground. Now I'm not going to ground the scope. And the reason for that is because this is potentially a differential signal, is what I believe it is. And if it's a differential signal, I don't want to potentially damage the power cab. Let me make sure you can see that. Put them over here. But I don't want to damage the power cab by grounding its differential signal through the scope. So therefore I put this isolation on there. So I can plug that in. Okay, so everything's set up for this experiment, and I'm going to now take some scope images of what this signal looks like, and I'll explain what those images look or what they depict. After a few adjustments to my scope, I settled with this initial image. This demonstrates two things. First, it confirms my idea that the two conductors are in fact a differential signal having a reversing polarity between them. These resulting square waves are then some communication being sourced from the power cab. Second, by using the scope's vertical cursors, I'm measuring a pulse width of a single pulse to be exactly 100 microseconds. That measurement is displayed in the lower right corner of the image. It also shows that the data clock rate, or baud rate, is 10 kilohertz. This second image demonstrates several things about the power cab's differential signal. The duration of each group of binary pulses is 800 microseconds. Because a single pulse is 100 microseconds, then each group consists of 8 bits. Also, the trace in this image shows that the time between each group of data bits is consistently 3.2 milliseconds with one exception. The group in which all the pulses are the same is followed by only 1.65 milliseconds. With the differential signal, the pulse polarity is not an indication of a binary 1 or 0. A low-going pulse is actually a 1 and a high-going pulse is actually a 0. My guess regarding this scope trace displayed here that the low signal between data groups is actually where the power cab is not driving out any voltage on the differential lines. This is most likely where the power cab is looking for a response from an addressed remote device. Given that assumption, I believe that during this transmission pause, the signal is being weakly pulled up to like the V plus state, waiting for a low level start bit from the addressed device. Obviously, if no start bit returns after the delay period, it just goes on and issues another address. So I'm guessing for the content of each one of the displayed pulse widths, or let's say bit groups, that from left to right on the trace, that the first bit is correspondingly a start bit in each one of them, and it's a low-level pulse width. On the screen, you see a sequence of bit groupings, and at the top of each bit grouping is a proposed binary arrangement. And if I've guessed at all things correctly, I can propose now that what those binary arrangements refer to are addresses 3, 4, and 5. And how did I come by that? First off, there are, according to the documentation, address ranges 3 through 63 are permitted. If address 63 has to be represented in this, then I suggest that it takes 6 bits in order to represent 63 in binary. And so it would have to be something where there's a start bit, and then there's 6 bits, and then there's a stop bit. And I looked at a number of different scope traces and looked at patterns, and it would appear to me that there is no way of error correcting any of this. There's no checksum bit. So the way it would pan out for the bits that I'm currently showing at the 3 groupings, we have an arrangement of 0, 1, 1, 0, 0, 0, 0, and then of course the 0. And so the 6 bits for the first one that has this bit pattern, I called that 3. And how did I come by that? Well, in binary arithmetic, you have to have some positional notation that proceeds as 1, 2, 4, 8, 16, and 32. So if each one of these has a binary value of 1, that would equal 63, because you would add up 32, 16, 8, 4, 2, and 1. And that's 63. Okay? So looking at this pattern, you'd say, well, it looks like you've got 32 plus 16 for that bit pattern, but you said it was 3. And the reason why I said that is because I'm proposing that the bit order, this is not the most significant bit. This is the start bit followed by the least significant bit, which means the whole thing is kind of reversed, and it would lay in here as 1, 1, 0, 0, 0, 0. And in that case, now you have a 1 plus a 2, which is 3 from these two. So I did that with each one of them, and I came up with 3, 4, and 5. So if I guessed correctly about a lot of things, the addresses 3, 4, and 5 are the addresses being pulled by the the NCE Power Cab, and that seems to support my theories about just exactly what has taken place on this differential signal that the NCE is putting out. I just heard that Dan Thorne, superintendent of the Lehigh Terminal Railroad, is out in the yard and he's having a discussion with one of the engineers. Let's listen in. Dan, I forgot to put a like in for this video.
Why, Tom, you ain't done anything like that in 20 years.
Gee, Dan, I just forgot. It won't happen again.
Don't you let me see you around these yards? Go on, go on.
You know, Dan, he's gonna forget the light again. He's done it before.
He knows better than that. Why, I'd have to rule him off the road.
Wow, geez, I hope Tom never makes that mistake again. He's a valued engineer on the Terminal Railroad. It would be a shame to lose him. I think I have as much information about the Power Cab's RS-485 network that can be obtained by this experimentation. I was wondering if it would be possible to fully decode how NCE implemented their interface to communicate with additional cab controllers and then use the Arduino to provide that required signal output that would pass the JMRI data over to the Power Cab. However, not knowing what the correct response should be to an address pulled on the RS-485 network, it makes that very unlikely. I plan to use NCE's USB to Power Cab converter. It's part number 5240223. I'll show you here. This will be how I pass the serial data received via the Bluetooth channel to the Power Cab. This concludes episode 18, part 3 of JMRI via Bluetooth serial on the Fun with HO Scale Stuff channel. If any of this episode was entertaining or interesting to you, please consider adding a like. And if you want to follow along, please consider subscribing to this channel. Thank you for your time to watch and share with me my curiosity and interest in scale model railroading.